So, good morning. Welcome to class. It is May 14th, um, Thursday. Hopefully, this doesn't come as a shock to anyone, but your AP test is today at 3 p.m. You will be getting email to the email address you use for the College Board. Yeah, I know. It's the AP test today. Yeah, for all of you who had no idea. Um, so, yeah, you will be getting an email at about 2:30. And if you've already taken an AP test, please tell me up here if there's any other information I should know. But yeah, you'll be getting the email at 2:30. You'll follow the link, you fill out some personal information, and then the test will start at 3 p.m. Central Time. So yeah, just be looking out for that. If you don't get the email, you should be able to go and follow it and use your AP ID. But yeah, tell me if something is going wrong, and I can try to do whatever I can to fix it. But yeah, the link comes with the exam ticket. It should go to your email. So make sure you have the email address from your College Board. Yeah, the one you received 2 days ago. So if you haven't been getting AP emails, you need to talk to me now. Like as soon as we're done with class, you need to email me. You need to talk to me or tell me in class, and I can help you figure out which email address it's going to and things like that. So yeah, if you haven't done the AP exam demo, you have to do that right now. You need to do the exam demo to make sure that you're actually able to upload your answers. So again, if you're going to use a computer, I would suggest either typing into a text file and uploading the text document or Word document, or copy and paste from the Word document onto the text box. Make sure you save throughout, right? Don't like forget to save and then close the document and it disappears. Um, and I think, and if you're doing it on your phone, if you're going to take pictures, I would suggest doing it on your phone or an iPad. Definitely make sure you have access to camera. And I think, Evelyn, you were the one talking about apparently you can't upload .heic pictures. Yeah, so if you're taking a picture from an iPhone or an iPad, look for Evelyn's post in the stream. You need to take your picture in, I think, JPG is what it needs to be. Um, yeah, so make sure it's doing that. Yeah, I wouldn't risk them being able to read your handwriting. I would suggest, if at all possible, I would suggest trying to type it out on a computer, um, and all that. You can't see, well, as long as it's taking the picture as a JPG. Um, is there something? Yes, and if you've already taken an AP test and there's something you figured out, please write that in the text right now, or you can talk, like you can put it into the stream. But yeah, you can all put anything you need to in the stream. All right, so yeah, those are the things coming up. AP test. I'm gonna be here until maybe 11:30, and then I'll come back at 1, and then I'll be here until like maybe 1 to 2 or 2:15, and then you'll take your test, and then I'll be back up at about 4. So if you want to come by and talk about everything, then yeah. Um, Yeah, the other thing is, if you use your camera, it can't be a live video or a live picture. You have to make sure to actually just take a photo and turn off the live. It wouldn't take that one either. But yeah, these are all things that you'll figure out if you actually do the demo. So you have to go to the demo. The link has been posted so many times. Do the College Board demo. Practice your actual submission process. Practice the submission process you plan to use for the test. Do that several times and get your setup down. That's probably the most important thing, because it doesn't matter how much you know if your uh, submission process doesn't work. And don't be waiting till the very end to submit things. Again, you have that 5-minute interval to submit things. Don't wait until like the last 30 seconds to try to submit things. That's how things end up not getting submitted. All right, so again, questions, put them off to the side. I'm going to start off with this sample question that I guess I just completely missed and didn't see. So we're going to do this one first. Yeah, so I could see that. Make sure you're actually logged into all of your correct accounts and everything. If you want to paste the response, I didn't see anything about having to include your ID number and initials. If you paste your response, you might as well do it. Just type it out once and then have that in copy and paste, and then just do that when you upload them. I don't think it really matters, but you can. They're not going to take points off for doing that. It's not like they're going to see that and think, oh, this is part of your response. All right, so let's go into this one. Vertical spring. A lot of you kept asking about vertical springs. I don't know if this is why, but we'll go through this. So this is a 15-minute question. So 15 minutes, 15 points. This is going to be your second question. It'll go on for 15 minutes, and then after the 15 minutes, it'll pop up with a submission time where you can submit it within 5 minutes. All right, so we have springs here. So a spring with an unstretched length L1 right here is hung vertically with the top end fixed in place. A block of mass capital M is attached to the bottom of the spring, is attached, shown in figure 2, and the spring has a length of L2 greater than L1 when the block hangs at rest. So this is where the block hangs at rest. The block is then pulled downward and held in place, so the spring is stretched to a length L3 greater than L2, is shown in the figure 3. The student releases the block. Consider the time during which the block is moving upward towards its equilibrium position, and the spring length is still longer than L2. Indicate whether the total mechanical energy is increasing, decreasing, or constant for each of the systems listed below, and explain why. All right, so first of all, let's kind of just look at this figure and see what's going on at each of those points. So before I even start, I'm just going to be looking at this. You obviously don't have to write these all out on your AP test. Just some good things to look at. Then we put the mass on there, and this thing hangs at rest. And then this length is L2. And then we go and we stretch the spring a lot down here. And this is L3 stretched. So L1, this is where the spring is without any masses on it. So what is this position? Equilibrium. Let's be more specific. This is the equilibrium for the spring. So this is the equilibrium for that spring. And we know it's equilibrium for the spring because the spring is not stretched or compressed. And at the equilibrium for the spring, our displacement from spring equilibrium is 0 meters. Our spring force is going to be spring constant times displacement. So our spring constant is going to be 0 newtons. All right, so that's our spring equilibrium position. What's happening here when the mass is just sitting there, hanging at rest? And again, hangs at rest. And the key thing here is it's staying at rest. So it hangs there, it stays at rest. So what is this position? So this is the equilibrium for the mass spring system. I like how you put that. So mass spring system equilibrium. So this is when our forces are balanced, right? We have our spring force up and we have the weight down and our forces are balanced. So this is when our spring force is equal to the weight of the object, at least the magnitudes are equal. They're in opposite directions. All right, and then we pull this down, we stretch it. What's happening here when we stretch this all the way down? So now we stretch the spring a lot. Now we have a really big spring force and we have the same weight as before. So here we're going to have the maximum displacement from equilibrium. And the equilibrium I'm looking at, when we're looking at both of these, this is going to be, when we're looking at the mass on the spring, this is going to be the displacement from the system equilibrium. So maximum displacement from the system equilibrium. So that means we have the maximum net force, and we have the maximum acceleration when we let go. And this is going to have the maximum spring force. I put it under the, this is number 2. I put this as an attachment under today's class. Sample question 2. So yeah, 514 class, AP exam sample question. All right, so all of that is back information. So now we can start thinking about this. The student releases the block. Consider the time during which the block is moving upward towards its equilibrium. So we release it from point 3. The string length is still longer than L2. Would displacement from the system's equilibrium, L3 minus, yeah, the displacement from the system equilibrium would be L3 minus L2. All right, so the string length is still stronger than still longer than L2. So we've released from 3, we've released from here, but we still haven't made it to 2 yet. So which force is bigger at this time? The spring force or the weight, if we were between L3 and L2? It's still going to be the spring force, right? Because this is when our forces are equal, but whenever we're not quite there, our spring force is still going to be bigger. When we're below this, our spring is stretched more, so we have a bigger spring force than we have a weight. So between L3 and L2, our spring force up is still greater than our weight down. So we have a bigger spring force up than weight down, and we released it. We haven't gotten to L2 yet, so we're also moving upward. So both of these are going to be important. So the object will slow down at the top. Yeah, so whenever we're going here, so we're going to be moving towards equilibrium, we're speeding up. When we go past this point, all of a sudden our spring force is getting smaller and smaller. So yeah, above L2, we have a smaller and smaller spring force, bigger and bigger weight. So we're going to be accelerating downward. So between L3 and L2, bigger spring force than weight. So we're accelerating up. And then between L1 and L2, we have a bigger weight than spring force, so we're going to accelerate down. So indicate whether the total mechanical energy is increasing, decreasing, or constant for each of the systems. So for system A, we're just looking at the block. What units are on the AP test? 1D kinematics, 2D kinematics, forces, energy, momentum, circular motion in orbits, simple harmonic motion, and rotational motion. So A, we're just looking at the block only. What type of energy are we looking at if it's just the block only? Yeah, so 7. It might be 8. Sometimes they say like forces on a single object, forces on a system of objects, a few in there that they can split up into 2 different topics. So if we only have the block, what type of energy can only the block have? So that's going to be kinetic energy only. So this is kinetic energy only. So as we move towards equilibrium, what's happening to our kinetic energy? Well, kinetic energy, we're just looking at speed. Are we speeding up or slowing down as we move towards equilibrium? our spring force is bigger than our weight. So we're getting pulled upward and we're moving upward. Or we could just say we move toward the equilibrium, the system equilibrium. And that means that the block speeds up. Anytime we move towards the system equilibrium, we're going to speed up. Oh, yeah, we already did one in a previous class. So the block speeds up. So the kinetic energy goes up. So kinetic energy increases. And total mechanical energy increases. So they're usually going to start out with kind of a more conceptually easy question. Well, just the block, we're only looking at kinetic energy. The block moves towards equilibrium. If the block moves towards equilibrium, it speeds up. If the block moves away from equilibrium, it slows down. So because we're only looking at kinetic energy, we're moving towards equilibrium, we speed up. And we speed up, so kinetic energy increases, and total mechanical energy, just the block, increases. B and C is where things start getting really tricky. So B is talking about system 2, which is the block and the spring. Now kinetic energy and spring potential energy. So now total mechanical energy is going to be equal to kinetic energy of the block plus spring potential energy. So let's kind of look at what's happening. When I release this, what type of energy do I have? At L3, all energy is... What type of potential energy, though? Yeah, all of the energy is spring potential energy. Now, we can put our height at 0 wherever we want, but a lot of times we're going to call our height 0 at our lowest point. So it kind of makes sense to call this lowest point down here, height equals 0 meters. All the energy is spring potential energy. So we're going to call height equals 0 meters at L3. That's going to make things a little bit easier. Then putting the potential energy at 0 on the ground. Gravity plus force applied is the spring. That's not complete. So this is right when we're released, though, right? We're released from rest. Yeah, so no kinetic energy. So all of the energy is spring potential energy. So we have no kinetic energy because we're not moving. And we're going to call L3 height equals 0 meters, which is going to mean there's no gravitational potential energy. All right, so at L3, all the energy is spring potential energy. What happens as we move towards L2? So as the block moves toward L2, no gravitation. It's not no gravitational potential energy because he was holding it. It's no gravitational potential energy because I can call my height 0 anywhere I want, and it's usually best just to call my lowest point 0 height, and that's going to make things easier. Okay, so as the block moves towards L2, we're going to see the spring potential energy is converted to kinetic energy. And where does some of the energy also go? Is it losing height or gaining height? If I pull the spring down and I let go, which way is it going to move, up or down? it's going to move up. So it's gaining height. So what's happening to its spring, or to its gravitational potential energy? So kinetic energy and gravitational potential energy, because it speeds up and the height increases. All right, so spring potential energy is turning into kinetic energy and gravitational potential energy. Both of these are going up. But we're talking about total mechanical energy as kinetic energy plus spring potential energy. So as the total mechanical energy, yeah, this was going to be helpful for C, but it's going to be necessary for B. So is our total mechanical energy for the block and spring increasing or decreasing? Yeah, it's going to decrease. So the total mechanical energy for 2 is going to decrease because energy is lost to that gravitational potential energy, right? So we are gaining kinetic energy, but we're losing spring potential energy to kinetic energy and gravitational potential energy. So gravitational potential energy is a place we're losing this mechanical energy to, but we're not accounting for it. So we're losing energy outside of the system. We're losing the energy to the Earth. Because you can think of it as I pull something up, the force of gravity is also pulling up on the Earth. So I am technically pulling up on the Earth as I do this. Is everyone okay with that one? That's probably the hardest one on this. B is the hardest part of A, B, and C. It's one of the ones I had to look at for just a second to get it right. Yeah, the energy also goes to the Earth and it's not getting counted. So because we're converting some of the energy to potential energy and we're not including the Earth as part of our system, we need the Earth to have that gravitational potential energy. So yeah, it's not being counted because we're not talking about the Earth. And then C, I would say, is probably the easiest one. This is how we normally account for. Actually, no, it's not. It doesn't include the spring. What am I saying? C, I didn't read that well enough the first time I glanced through this. So C is the total mechanical energy of the block and Earth. Block, Earth system. All right, so what energy is included in my total mechanical energy? So this is going to be the kinetic energy of the block and gravitational potential energy. Now we're not including the spring in the system. So no spring potential energy. No spring in the system means no spring potential energy being accounted for here. It gains, yeah, it does gain more than A. Yes, it actually does. But it doesn't say that we actually have to compare them. We just have to indicate whether it's increasing, decreasing, or constant, and explain. So you are correct. C gains more energy than A does if we were to compare these. So we would look at this. So again, at L3, we have all spring potential energy because our height is 0 meters and it's at rest. That means our gravitational potential energy is 0 joules and our kinetic energy is 0 joules. So we let go and the mass speeds up and the height increases. Right, so we let go, the mass speeds up, the height increases, so we have our kinetic energy goes up and our gravitational potential energy goes up. I really don't have to talk about my spring here anymore. I could say that the spring potential energy is what's turning into these. So I could say the spring potential energy is going into kinetic energy and gravitational potential energy. These are taking from that spring potential energy. So these are the only two that are included. So kinetic energy goes up as we speed up, our height goes up, so our gravitational potential energy goes up. So that means the total mechanical energy for that system 3 increases. And then if we were to look at a system of the block spring earth, that would remain constant, right? So total mechanical energy for the block spring earth system would remain constant because that's the gravitational potential energy, spring potential energy, and kinetic energy. Everyone okay on these? All right. Yeah, just try not to overthink them. Just if it's talking about an object, that thing can have kinetic energy. If it's talking about the object and the earth, then you can have potential energy, gravitational potential energy. And then if you include something like a spring, then you can have spring potential energy. Yeah, so total mechanical energy for the block earth system increases. Another way of looking at this is we could say the spring is external to the system. The spring is losing energy, or the spring is providing a force on the system. So spring is doing work on the mass and the earth. So you could also say that. So there's a few other ways you could go about talking about this. All right, so I'm just going to sketch out this that we have here. That's on this next part below. We have L3, L2, L1. Then we have here, which is period over 2, and then we have period right there. And now, does anyone notice something weird about this graph? It stops. I mean, yeah, obviously it would keep going. They just represented one period. So yeah, they did only represent one period of the motion. It is a cosine graph. L3 is at the lowest point. L1 is at the highest point. So why is the lowest point at the highest up here and the highest point is at the lowest point here? Yeah, the longest length. So you notice they measured the length of the spring, not the height. So this is a measure of the spring length, not the height. Just a thing to kind of this is what makes this AP test so hard. Is they're like they do things like this. So this is actually at the lowest point. At the lowest point, the spring has the longest length. This is at the middle point, the system equilibrium. And then this is at the highest point because the spring is stretched the least. Are we okay with this? Yeah, so this is one of those things, again, I glanced through this. I actually didn't notice this until right now. But yeah, I noticed it when I looked at this one more time. This is honestly what makes the AP test hard. They can do things, just look carefully. At the end of the day, if you mess something up like this, it's a good chance the rest of the world messed that up. And the only people who get a 5 are the people who don't mess that up. judging your physics knowledge on 2 questions. Honestly, my biggest gripe with the AP test is things like this. They're like doing a low-key IQ test on you as opposed to your judging your physics knowledge. In Asia, oh, it starts at 2 a.m. Yeah, that's pretty terrible. I didn't actually look at the other time zones, but yeah, that's pretty terrible. A lot of it's the worldwide people. There's that international AP test. Yeah. All right, so looking at this, so now we want to know during which time intervals, if any, is the weight force acting on the block greater than the spring force acting on the block. So D, we pretty much want to say when, and pretty much anytime they're talking about force, they're talking about magnitude of the force. So when is the magnitude of the weight of the block greater than the magnitude of the spring force? I mean, normally they would take it at a different, like at the same day, but it's an international version of the test. So yeah. So when is the weight of the object greater than the spring force? So there's a few ways of doing this. When is the weight going to be equal to the spring force? So at equilibrium, so we know at L2, the system equilibrium, is when the weight is equal to the spring force. So this is a nice spot to kind of divide up our graph. So it's either going to be above this point or below this line. So either above this line, the weight is bigger, or below the line, the weight is bigger. So why are you saying L1 is when the weight is bigger than the spring force? So you're saying down here, below the line. So when it's above equilibrium, all right, so there's a few ways of going about this. So we have at our equilibrium position. So we could say, in order for the spring force to be small, so for a small spring force, we need a small display. Actually, that's not going to be the best way to go about it. Yeah, how should I? There's a few ways I was thinking about going about this one. You can go about displacement, but that's going to have to be displacement from L1, and it's going to get tricky talking about displacement here. Should I put this in terms of forces? And because there's the way I would do this, which has to do with like this is concave down, concave up, concave down, and which way the forces are. And that's how I would probably answer it, but I don't think that's the best way to answer it for y'all. So let's say, yeah, when the block is higher than L2, the spring is stretched less from its equilibrium position and has a smaller spring force. Something like that. So when the block is higher than L2, the spring is stretched less from its equilibrium position. We're talking about the spring equilibrium, right? This is the system equilibrium. The highest point is the spring equilibrium. So we want to get closer to that spring equilibrium. At L2, we know the spring force is equal to the weight, and then that means between L2 and L1 are when that spring force is going to be less than the weight, right? Because we want to get at L2, this is when the forces are the same. So that means above that, they're going to be smaller. And it wants an interval. It wasn't clear. It just says during which intervals, which I really dislike. I think they're trying to get time intervals. Because normally when they're talking about interval, they're talking about the interval of time. So what would that time interval be? So the height intervals would be between L1 and L2. Or the time interval would be 1/4 of the period to 3/4 of the period. And then, yeah, can we say the block is trying to accelerate downward, meaning, yeah, so that's the other way that we would have gotten this. So we can look at this graph. This is length versus time. So we could say right here is concave up. So that's positive, but our graph is upside down. So yeah, we could go about this. So we could say that here we have a downward acceleration, because we really kind of have to flip our graph to get our positions. So here we would have a downward acceleration. If we have a downward acceleration, then our spring force is bigger than our weight. That's the other way to talk about this. So yeah, so Kelly, that's how I was thinking of doing that. Can you include T over 2? Yeah, you can include T over 2, because T over 2 is when you have the absolute least spring force. That's where in fact, L1 is where they put the equilibrium position for the springs. That's where it would have 0 spring force, according to this system. The ones you just can't include the endpoint. We can't include the endpoints here. But yeah, the other way is going about accelerations. And so, yeah, if you're above the equilibrium position, you're going to accelerate towards equilibrium. So you could say above the equilibrium position, you accelerate back towards equilibrium. So between in this interval, we accelerate down. If we're accelerating down, then we have a bigger weight than spring force. How do we know if the block speeds up or slows down downwards? Yeah, so that gets real messy. Let's go through the entire motion of the spring. Yeah, let's do that. So we let it go. So we let it go at L3, and then it moves up to L2, and then it stops at L1 before heading back down. So going from L3 to L2, we're going to have a bigger spring force. So spring force is bigger than our weight, which means we accelerate up. We let go, so we're also moving up. Our acceleration and velocity are in the same direction, so we speed up. Then we go past this. We go from L2 to L3. Now we've moved past equilibrium. Now all of a sudden our weight is bigger than our spring force. So we have more force down, so we're going to accelerate in the downward direction. But our inertia keeps us going up, so we're still moving up. So accelerate down, move up, acceleration and the velocity are in opposite directions, so we're going to slow down. Then we're going backwards. What did I say? There should be L2 to L1. Sorry about that. Then we get to L1. Now we go from L1 and we move back down to L2. So from L1 moving down to L2. Our weight is still bigger than the spring force because we're above equilibrium. So we're accelerating down. But we reach that point where we're now moving back down. So we accelerate down and we move down. So we accelerate down, we move down. So acceleration and velocity are in the same direction. So we speed up. And then we go from L2 down to L3. So now we've gone past the system equilibrium. Now our spring force is going to be bigger than weight again. So our spring force is bigger than weight, so we accelerate up, but we're moving down. So we accelerate up while we're moving down. So acceleration and velocity are in opposite directions. That means we're going to slow down. Is one way of doing it. Or we can go through and we can talk about if we move toward equilibrium, we're speeding up. If we move away from that system equilibrium, we slow down. Acceleration is always pointing towards the mass spring equilibrium. That's the entire thing about harmonic motion. That's the entire definition of harmonic motion, is your net force always points back towards the system equilibrium, which means your acceleration always points back towards the system equilibrium. That's like literally the definition of harmonic motion. Because the block slows down but is still moving down, spring force, the block slows down, but is, yes, if the block slows down and is moving down, spring force is bigger. Yeah, I mean, it's just one of those things that I like mentioned a few times, but I try not to get too bogged down in definitions. So yeah. All right, questions on this one? And honestly, you could have answered this while ignoring that graph for the most part. And you probably would have been better off ignoring that graph because it was upside down compared to what a lot of you expected. It was up to, in all fairness, it was upside down compared to what I would expect normally. So don't get too down on that if you didn't see that. All right, so then finally, now when the block reaches its lowest point after oscillating several times, the student attaches the new block mass lowercase m less than mass m to the block of mass m without exerting a noticeable force on to the block of mass m or changing the energy stored in the spring at that instant. Isn't that fun? So pretty much all they did was increase the hanging mass when it was at the furthest position. Stop zooming in and out. But yeah, pretty much all they did was increase the hanging mass while it was at its lowest position. So in a clear, coherent, again, paragraph length response doesn't mean paragraph. Paragraph length response is usually going to be about 4 or 5 sentences. Oscillating is just up and down or back and forth. Think of a fan, a personal fan that oscillates. If you put the oscillate setting, it just moves side to side, back and forth. So a repetitive back and forth motion or repetitive up and down motion type thing. You can reference equations. So you can write equations. You can talk about equations. They just don't want you to focus on the math. Explain how the graph of length versus time will change and why. When is the test? The test is at 3 p.m. And yeah, the camera actually is oscillating. But yeah, it's at 3 p.m. You should get the email at 2:30 in order to log in. Yeah, get to the exam at 2:30. If you haven't been getting College Board emails, I need to know about that now. Like now, I actually need to know about that like weeks ago. But yeah. All right, so what's going to change here? I put a larger mass on there. Oh, sorry. Joking, it's hard to tell sarcasm from text. So period will change. So yeah, that's the first thing to think about. So we can reference equations. We are talking about a spring. Period of spring is going to be 2 pi square root of mass divided by spring constant. Now, if you're typing this, we can just type it like this, do a capital T and just a lowercase s. You don't even have to put a subscript. I would say that's kind of obvious. 2 pi times square root of mass divided by spring constant. You can type that pretty fast. All right, so we have this. So we know our mass increases. So mass increases, so what happens to our period? That works. I would put the pi in parentheses just because it looks like pi squared, like it's all like a combined together thing. If you put the pi in parentheses, it makes it a little bit more apparent that it's different. Make like a document for the formula to copy and paste. You can try that. I don't know how well it's going to copy and paste in the text box. But yeah, mass increases, which means the period of oscillation increases. So we really want to explain how the graph of length versus time will change. So what's going to happen to the graph? We're looking on the x-axis. So how is the x-axis going to change? I would say the graph gets wider as the period takes more time. So yeah, it stretches horizontally, something like that. Horizontal stretch is a little bit fancier way of saying wider. Is that the only thing that's going to change? Amplitude, yeah, the amplitude and equilibrium, those are all going to change, right? So the more hanging mass adds more weight, and the system equilibrium will be lower. So the equilibrium changes. It's going to have a greater amplitude. So we have a larger weight. Now, this is a really weird thing. I think they're trying to say they put it at the same amount. This really all depends. It's such a weird thing. I think they're trying to get at that they release it from the same point below, so it's going to go up and down to the same point, actually. It all depends how much mass they add. Actually, no, we can go through this. Never mind. This is going to be different. Let me think a second. That's never a good sentence whenever I'm saying let me think a second, because that means a lot of you, it's going to be tough. So there's a reason that they're saying they're adding a smaller mass. All right, now I see this. So yeah, so the problem with this is that spring force is going to be spring constant times distance from equilibrium, right? So the equilibrium position changes. Yeah, so if I'm going to write this down here. Let's say if I double the mass, where is the new equilibrium position going to be? So if I double the mass, that means the weight doubles. At the system equilibrium, I know the spring force is equal to the weight. So I could say the K times displacement is equal to the weight. But my weight doubles, right? So if I double my weight, my equilibrium position would double. My spring constant is constant. So that means 2 times the weight. If I double the mass, I double the weight, and I would double the displacement from the spring equilibrium to get the system equilibrium. So yeah, they didn't give us enough information for this. They did not give us enough information. Yeah, it's not enough information. Because yeah, so I would say if the L1 to L2 is an equal change in length of L2 to L3, we would know. I think based on the graph, though, is this graph to scale? Yeah, this graph is to scale. It has to be to scale. But they didn't put numbers here. So I think this is what they're getting at. I think they're saying if I double the mass, I'm going to double the distance from to the new equilibrium position. So normally it goes from, when I just put the mass on there, it goes from L1 down to L2. So that would be the new length of the string with just mass M. But I think they're getting at, based on the graph, it looks like this is double. So down to L3 would be if I were to put 2M on here. But I put less than 2M, right? Because I put a lowercase mass m. So my equilibrium position should be somewhere down here. So this would be m plus a smaller mass. This would be the new system equilibrium position. Wouldn't the right side of the graph change because yeah. That doesn't matter. So what's going on here is, because we added a smaller mass, the new system equilibrium is going to be lower. Okay, so yeah, this is what's going to happen. All right, so we have more mass, therefore more weight, therefore lower system equilibrium position. Now, because we added a smaller mass, that means the lowest point won't get lower. So this is where I'm having to make an assumption here. I think this is the assumption they were having you make. So looking at these two things, so we stretch to L3 whenever I pull this all the way down. L2, it stretches two of these when I add mass M. If I had a smaller mass M, it's going to go to around here. So I would still have to stretch the spring down to let it go. So what they're getting at by adding a small mass is they added a mass that was small enough to where the equilibrium is not going to be lower than L3. So that's the whole point of what they're saying when they add a smaller mass than M, is that the distance is not going to end up greater than this distance, is what I think they're saying. But they weren't clear enough. They did not give enough information here. So I am having to make an assumption here that if I add that small mass, it's not going to end up at a greater distance than where L3 was. All right? Does that make sense? This is an important thing. Okay, so yeah, this is a 15-minute question. Yeah, so from here to here, L1 is my equilibrium position. When I add a mass capital M, I go to here. If I were to add a mass capital 2M, I would end up at L3. I would end up twice as far from equilibrium, right? So when I add a mass m, I go 2 blocks up. So if I were to add 2m, I would go 3 blocks up, and I would end up at this L3 position. So based on how this graph is shown, if I double the mass here, I will end up at L3. Okay? But because I am adding a smaller mass than mass m, I am going to have a new equilibrium position somewhere between L2 and L3. So because my new equilibrium position is between L2 and L3, the masses are not going to sink down below L3. That's the key thing. So when I release from here, it's going to oscillate between the equilibrium, go to past the new equilibrium here, and then the lowest point is still going to be L3. So my lowest point in the oscillation of the spring is going to stay the same. Based on how they drew this graph, the only way I can interpret this is between this graph. So when I put mass just capital M, my equilibrium position is L2. If I were to double that mass, my new equilibrium would be L3 because 1, 2, 1, 2. But because I added a smaller mass, my new equilibrium position is going to be between L2 and L3 with the new mass. So yeah, more mass, more weight, lower system equilibrium position. We added a smaller mass, so the lowest point will not get lower. So it's going to have a small oscillation. So this will be a small oscillation from point L3 past the equilibrium between L2 and L3. So another way of putting this is we're going to have a shorter graph, so a lower amplitude. So the graph is going to be a lower amplitude. Through an equilibrium position between L2 and L3. That's a good question. This only actually works if this graph is to scale, which it should be because it should be symmetric. But if this graph isn't to scale, then this entire reasoning fails and they didn't give us enough information. And by the way, yeah, I'll make a new graph. By the way, this is how they differentiate between like 3, 4s, and 5s. Is they're going to ask a really hard question like this towards the end, where they like flip the graph all around and they make a really difficult question like this where they're like really vague. But yeah, so before we had L3, L2, L1. So these were our positions. And then whenever we do this, so this was our old equilibrium position. But now we put more mass. And so now we're going to have a new equilibrium position. And then L3 is still going to be the lowest point. Still the lowest point. And then we had our old period of oscillation, and then our new period of oscillation is going to be longer. So it's going to be all the way around here. It's going to go not quite so far, and then not quite so. So it's going to be longer and shorter. So wider and less tall. You're not supposed to talk about the questions immediately after, but they will release them. But yeah, I'm just going to be there more so you can like discuss it and ask general physics questions about nothing in particular. But I'm not going to be there during the test. I'm not going to help you out during it because that would be a fast way to get fired. But yeah, after the test, they should release the questions a few days. Like usually it's 48 hours after the test, and I can go through it then. All right, so this one took up way more time than I expected it to. Yeah, I'll go over it every time after they release. I'll go over it. Why the lowest point is L3? Because yes, that's the easiest way to think of it. The lowest point is still L3 because that's where it's released from. Yeah, I mean, I also won't record it. But, all right. Yeah, D and E, those were rough. All right, so I guess I don't have as much time. If you upload this, I'll give you some points. Yeah, that was a rough question for 15 minutes. A, B, and C should have gone relatively okay. And then just how they made that graph, the wheels probably started going off from there. But yeah, so any other questions? Because yeah, we kind of are out of time to do the thing I was planning on doing. Yeah, that concept map. You can still do it. That would be a really good thing to review, to work on. Do you want me to start like a concept map for you? And go through it? It's just something I've seen other physics teachers do as a review. But yeah, so a good way to review. So you would start out with something like physics in the center. And yeah, I'll pull up your question in a second after I get this started. So we can talk about physics. We can go through a few things. I would say probably the biggest things in physics would be the Newton's 3 laws. That's going to be the biggest thing we see on our test. And then we can go through this. We can say our like first law. So Newton's first law. And that would be something like constant velocity if net force is 0 newtons. And we could relate this to kinematics. So we could relate this to like accelerations and things like that. We can also relate this to like second law, where net force is equal to mass times acceleration. And we can relate this to kinematics. This relates well to kinematics and those equations, right? So we can talk about 1D kinematics or 2D kinematics. So 2D kinematics in the x direction, we know our acceleration in the x direction is 0. And then we can also relate that here. So just kind of a concept map going through things like that. Yeah, that's fine. I mean, I was going to spend a little bit more time on it, but that question ended up coming up, and then let me see. Here, let me answer Tam's question. Which question did you have the question on, Tam? I see it right here. Problem, use formula, square GMO. Yeah. Oh, wait. You're talking about 3, right? Yeah, 3A. All right. So let's go through this. Someone put up one of the concept maps. I forget who actually put it up there, but I like looked at it real fast and they like posted it in the comments, and I thought it was pretty good. I didn't see anything. Was it Jocelyn? So yeah, so we have Boo. But something like that's just a good way to kind of like it's more so for you a good way to like kind of organize your thoughts. Um, but yeah, so Space Probe A orbits in a geostationary orbit directly over Jupiter's equator, 90,000 kilometers above the surface. Identical Space Probe B sits on the surface of Jupiter. Which probe, if either, has a greater speed, greater acceleration, and then yeah. But yeah, so which probe has a greater speed? One is on the sits on the surface of Jupiter. It kind of didn't give you enough information. But the one orbiting is going to be going faster. And the thing to remember about this equation, this is for the speed of an orbit, is going to be square root of acceleration of gravity times mass of the planet divided by radius. If the thing is on the surface, it's not an orbit. I am sitting on the planet Earth. I am not in orbit. So the speed sitting on a planet is going to be small, right? Because this equation only works to get you into orbit. So that's why the thing in orbit is faster. Orbit is going faster than on the surface. So yeah, if you're on the surface, then yeah, you will have to use the speed as 2 pi r over the period of rotation for the object. This equation always works. This equation only works for circular orbits. And then which one has a greater acceleration towards the center of Jupiter? Well, yeah, that's going to be the one on the surface. So how we can get acceleration due to gravity? We can just do force of gravity equals force of gravity. Amazing. mg is equal to gmm over r squared. Mass of the object does not affect acceleration due to gravity, if you don't know that by now. Yeah. It's a question that Tam put up. Space Probe A is in a geostationary orbit above Jupiter's equator, and then B is on the surface. And it's pretty much like, so which one is going faster, the one in orbit or the one on the surface? Well, the one in orbit is going faster. If a planet was spinning at orbital speed, the planet would rip itself apart. So that's not it. And then B is which one has a greater acceleration towards the center of Jupiter, the one in orbit or the one on the surface. Well, acceleration due to gravity is just this. Well, they both have the same gravitational constant. They're both in the universe. They're both above Jupiter. So in order to get a large acceleration due to gravity, we'll want a small radius. So a larger acceleration due to gravity is going to be the one on the surface. You want to be closer. Yeah, I mean, Jupiter doesn't have a solid surface. We'll say it's like a balloon floating, which, by the way, it can't be any balloon. It would have to be. It would actually have to be a vacuum balloon. You can't even use hydrogen because it's mostly hydrogen. It's the answer key said it was A for greatest acceleration towards the center of Jupiter. Yeah, so they might be getting it sits on the surface. Oh my God. Okay, I know what they're getting at. They're saying we're sitting on the surface of Jupiter, so the normal force is balanced out by the weight, and so they're saying that the acceleration is zero. That's what they're trying to say. But Camille, Jupiter does not have a solid surface. So yeah, that's this is a silly question. You don't sit on the surface of Jupiter. So that's what they're getting at. If I'm sitting on the surface of Earth, my acceleration is 0 meters per second squared, even though my acceleration due to gravity is 9.8 meters per second squared. That's what my acceleration would be if I was in free fall. But yeah, this is secret. Yeah, I mean, there is a potential that the inner core of Jupiter is a solid metallic hydrogen. So there could be a solid metallic hydrogen surface, but by the time you got there, you'd be like completely crushed by the absolute forces. Calculate the acceleration of an orbiting satellite, like this. Either that, or you could do the orbiting satellite. It would be centripetal acceleration as speed squared over the radius. And we could substitute this in, and we would get this exact same equation again. So that wouldn't do anything. Or yeah, you would just go to the bottom of Mariana's Trench and like be okay. And we could also substitute this in, so we could do speed squared is 4 pi squared r squared over period squared, and then we could substitute this in here, and then so our centripetal acceleration would be 4 pi squared r squared divided by r period squared 4 pi squared r divided by period squared. So we could also do that. Any other questions? I'm kind of done with that question. There's like a lot of silly things happening there that don't actually work how it actually works. Although, I guess there is one good thing that's going on here. The force of Jupiter on Space Probe A is equal to the force of the Space Probe A on Jupiter. They are doing a Newton's third law here, right? Jupiter pulls on Probe A with an equal and opposite force that Probe A pulls on Jupiter. So that would be a good thing to talk about. So that would be like I pull up on the Earth with the same force the Earth pulls down on me. So those are a good Newton's third law reaction. How is the satellite turning when normal force equals weight? So this isn't a satellite. Notice it says the word probe, space probe. So you can put a space probe on the surface of a planet. So it's not in orbit. So we wouldn't call it a satellite in orbit. It's just a probe sitting on the surface of a planet. So yeah, the moon is a satellite. Yes, all of our satellites are actually artificial satellites. All right, so I don't want this video to be too long because I want some people to actually maybe watch it. So I'm gonna stop recording here. So again, if you want to stick around, just stick around. I'll stay here for a little bit. But yeah, so if you've somehow forgotten your AP test is today at 3 p.m., you should get an email at 2:30. You should go there and log in and go there as soon as you possibly can. Make sure you get some rest. Don't push yourself too hard trying to study. But yeah, just kind of do your best. Honestly, no matter how you do, I'm like proud. Just try, and I'm happy for you. I'm not going to judge you. I'm not going to be upset. I'm not going to be disappointed. So yeah, feel free to stick around, and I'll stay here. But yeah, have a good day and just do the best you can.